Hey, so today I'm going to talk about how I see the Hubble Doppler shift and redshift and the CMB, and why I don't see either of them as being any kind of evidence at all for the Big Bang. So let's start with the Doppler shift. Okay, the Hubble Doppler, whatever you want to call it. The fact, and other people have addressed this, the fact that everything as it gets further and further away from us gets redshifted. Okay, well, duh. It seems like you'd kind of expect that to happen as soon as you take relativity to effect. Right, as long as relativity is a thing and space has variable densities, okay, and space is more contracted near gravity. It's a denser form of space. So Hubble Doppler. Okay, here's us. And here's the universe expanding away from us. Well, not expanding, existing away from us, right? And since this is a two-dimensional model, we can sort of say, okay, well, like, pick any surface area, and that will represent isomorphism, an amount of mass, right? So you go, okay, well, here's pretty local universe, and the mass nearby us is not that much, but as you go further apart and look at this, what's the mass of this compared to this? Oh, this is like I don't know, we could do some math, it depends on the angle, but the fact is, look at this, this is like twice as much mass, 3 times as much mass here as here. As you get further away, the mass of the universe around you grows larger. Since that mass grows larger, it pulls on space away from you because the mass is over here, not where you are. And in fact, there's infinity mass over there, or, almost infinity mass, Schwarzschild radius. We'll get to that. So, of course, space curves away from you. Redistance. Okay, and Eric Lerner and others have addressed this. That's really, it's like it seems to be like it's the geometry. Doesn't need a cause, it's just the unique geometry. I think it's a Einstein-Brand-Dicke model, but there might be tweaks. But anyways, it seemed to me like when I heard this, I was like, why do you need that? Doesn't that make sense? That instead, here's now, and this is base frequency, right? As you get further away, and this is limit, as you get further away in space, this is 13.8 billion light years, or billion years, okay? As you get further away, space gets bigger, it pulls space away, the universe gets more away from you, there's more of it. We live inside a singularity called the observable universe. Okay, the mass of the observable universe, you plug that into a Schwarzschild radius device, and what you'll get is 13.8 billion light years, because the mass of the universe creates a curve in space away from us so that we can never see more than 13.8 billion light years. It's not a hard thing. If we moved, this thing would move with us. Somebody who exists, this is a soft singularity, so to speak, somebody who exists here on the edge, somebody's in a galaxy over here. Granted, it's 13.8 billion or 13.5 billion years ago that we're looking at them, but because the universe is eternal, let's say they have a crazy civilization where everyone exists forever, or like they exist for like hundreds of thousands, billions of years, hundreds of thousands of billions of years. So anyways, so they, They can see us, and we can see them. The so-called expansion that is attributed to this shift in frequency downwards, and then there's a limit, and this is our visible limit, and this is the CMB, right? Basically. So this is, so we live in a weird fisheye lens universe, right? Like everything we see is smeared. And then this is gravity smeared. At this point in theory, right? I'm pretty sure you can check the optics math on it, but one single photon at this point ends up getting smeared across the entire universe. Okay, what we're looking at is the energy surface of the universe at, around 13.8 to 14 billion light years. Now, what I found interesting in looking at this, okay, and then of course there's all the galaxies and everything that are in between that the CMB has to come through, and that's where it gets any texture, let's face it. I don't even understand why that was a thing. As I said, you can look at Eric Lerner, and there's other people also. It's just like, okay, so this accounts for the redshift. Right now, let's look at the CMB and what that is. Okay, so that is, when you see the CMB and there's the origin of the universe, what I find really interesting is, according to neutron decay cosmology, there's a neutron. Neutron decays into a proton and an electron, right? A hydrogen atom. And then this will get compressed by gravity over time until it's forced to be a neutron, falls in, becomes a neutron star, the densest form of neutron possible, when all those neutrons actually have to occupy the same space. They can't, so they decay, and they become hydrogen, and then they fall again through time to become a neutron again. Endless cycle. Okay, and at the center point is this infinitesimal time, which is a shared compact dimension by all of us. But let's get back to this. Neutron decay. Okay, so you got the neutron. This is this is quark mass, right? This is like in the Big Bang model, I'm pretty sure. Like when you guys go through your timeline, it's like, oh, there was like this swirly quark mass, right? And then there was this period after that where it was the great separation or some stuff you guys have, okay, when this happened. And then there's a dark zone, which is when I say we have amorphous atomic hydrogen, which can't scintillate. It doesn't have a proper electron yet. It can't emit or absorb photons. It's just protons and electrons soup sort of thing. And then they recombine, and the proton gets its stable electron shell, and now first light. Okay, but this wasn't a billion years. This is a continual process. What we're looking at is the right now, well, not the right now, the 14 billion years ago of this process happening. Quark soup, separation, dark time, first light. And now this is hydrogen, and slowly nebula, blah, blah, blah. Stars, protostars, stars, evolution. Okay. This is just my thinking. It's just like, okay, well, that makes total sense. So, Hubble, Doppler, and CMB. This is how I see them. I know I'm crazy, but I just don't understand why we believe the CMB. Like, why we believe A, that the observable universe is necessarily the limits of the universe. There's no real good evidence for that, I don't think, yet. What we need to do is to be able to look for, I think what we should look for is sort of like duplicate mappings around the universe. Like, we're already seeing this gravitational lensing, but the gravitational lensing just gets larger and larger the further you go away. There's more mass to have interfered with that light. Our imaging gets worse and worse. As I said, it's like eventually like one photon in theory should be like one photon at that point, at the edge of our observability, is basically smeared across the entire universe, of course. And so the whatever the temperature is at the CMB, it's like that's the temperature of the universe. I mean, pulled down. It's all the energy of the universe pulled it down till it's, you know, very, very low frequency. Where can we detect? You know, it just gets pulled down. This is why my cardioid. Right? It's pulled down. This is us. Frequency shift until at 14 billion light years, which I guess might also be the average lifespan of a world line. Your hydrogen, it takes you 14 billion years or so to end up, on average, at an event horizon. And then you fall through, and then you emerge. It's just a continuous cycle. And this is gravity pulling harder and harder, smearing frequencies more and more, smearing the image more and more, until at this point we have essentially a almost dipole. And the amount of image manipulation that needs to be done, Robitaille addresses as well. Not that I'm only going to cite those two people. It's just that, you know. Anyways, this is how I see our situation, and that's why it's like I just don't see that any of this evidence for the Big Bang is as irrefutable as constantly made out. It's like nobody even says, oh well, this is one of the theories. No, like, boom, this is the way it is. Now we've got some tweaks to do, granted. We don't know what dark matter is. We haven't figured that out. We keep on grasping at straws, but, you know, none of the straws seems to hold together. You need to bind them into a really nice, some nice cordage. Using plasma physics, maybe. Anyways, peace out.